Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on November 24, 2025, about a week ago. It introduces a lightweight, open-source video generation model with only 8.3 billion parameters that still reaches state-of-the-art visual quality and smooth motion, while running efficiently on consumer graphics cards through a two-stage diffusion transformer and video super resolution pipeline. The paper is titled HunyuanVideo 1.5 Technical Report, and as we will see later, the results are really impressive for everyday creators and researchers alike. Also, the authors shared an official GitHub repo for HunyuanVideo 1.5. There you get full inference code, download instructions for the pre-trained checkpoints, a generate script with all the acceleration options, a detailed prompt handbook, comfy UI integration, example configs and videos, plus an early peek at the upcoming training pipeline. Alright, the introduction highlighted how crucial good captions are for video generation, and Figure 1 shows how the team actually trains that caption model in 3 stages. Step 1 performs supervised fine-tuning on curated caption data, so the model first learns to be generally sensible. Step 2 runs a ranking direct preference optimization stage, where a critic model scores multiple candidate captions and the system prefers the better ones. Step 3 applies OPA direct preference optimization with human correctors, which pushes the model toward rich, yet factual descriptions instead of hallucinated detail. Well, Figure 2 shifts from captions to the core generator and shows the unified diffusion transformer that powers all the text-to-image, text-to-video, and image-to-video tasks. Text first flows through multiple encoders, including a multimodal language model and a glyph-aware by T5 path, while images pass through a video autoencoder and vision projector. Their tokens merge into a shared sequence that enters stacked dual-stream blocks, where 3-dimensional rotary position encoding and either dense or sparse attention model space and time together. Alright, Figure 2 outlined the overall transformer layout, and Table 1 now pins down the key numbers that make that design work in practice. The model stacks 54 dual-stream blocks, which are the repeated transformer layers handling space and time jointly. Each block uses a model dimension of 2048 and a feed-forward dimension of 8192, so the network has plenty of capacity. There are 16 attention heads per layer, with head dimension 128, giving a broad but still efficient attention split across features. So, after defining the transformer backbone, Figure 3 explains how the system actually reaches crisp high-definition video. The pipeline first uses the base diffusion transformer to turn noise and a text prompt into low-resolution latent features. An UP sampler enlarges these latents, which are concatenated with the original ones, and pass into a super-resolution diffusion transformer. A variational autoencoder decoder then converts the refined high-resolution latents into the final 1080p video. So after the high-resolution pipeline, Table 2 spells out how the model actually learns across stages. The first 2 stages pre-train only text-to-image at 256p and 512p using huge datasets, 5 billion and 1 billion images. Stages 3 to 6 then mix text-to-video, image-to-video, and text-to-image, gradually increasing resolution, frame rate, and video length. The final 2 stages switch to continuing training, with just text-to-video and image-to-video at 480 and 720p, so the model focuses on motion quality and temporal coherence. Okay, after the training schedule in Table 2, Table 3 reports how the text-to-video system actually scores against strong competitors. The model leads on structural stability with about 80, which means scenes stay consistent across frames, and it also tops motion effects around 58. It sits in the middle for instruction following and aesthetics, behind VO3 on following prompts, and behind VO3 and Kling 2.1 on aesthetics. Visual quality scores are tightly clustered, so perceived sharpness and cleanliness are broadly comparable across all models. So, after comparing quality scores, Table 7 turns to raw generation speed without any engineering tricks. The table lists text to video runs at 480p and 720p with 121 or 241 frames and reports seconds per diffusion step. At 480p, each step takes about 0.91 seconds for 121 frames and 1.70 seconds for 241 frames. At 720p, sparse attention cuts step time from about 2.01 to 1.56 seconds for 121 frames, and from 5.51 to 2.95 seconds for 241 frames, which shows a very strong benefit on longer videos. So the big picture is that HunyuanVideo 1.5 shows you can match or beat many proprietary video generators with a compact 8.3 billion parameter model that still runs on a single consumer graphics card. That combination of open source code, bilingual prompting, and efficient sparse attention really lowers the barrier for serious video creation and research. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.